Dear Kavli Prize laureates, Kavli Foundation, Ministry, and Friends of Science. I would like to extend a warm welcome to all of you to this Kavli Prize laureate lecture in astrophysics here at the Science Library at Wilhelm Bjerknes House. Before we start, I would like to offer our congratulations to the University of Oslo. As the Vice Rector said, today it's 213 years since the university was founded in 1811. The Kavli Prize honors scientists for breakthroughs in astrophysics, nanoscience, and neuroscience, transforming our understanding of the big, the small, and the complex. Since the first awards in 2008, the Kavli Prize has recognized innovative scientific research from the discovery of CRISPR-Cas9 to the detection of gravitational waves. The Kavli Prizes have so far honored 65 scientists from 13 countries. 10 laureates have received the Nobel Prize after receiving the Kavli Prize. The prize was established in 2008 by Fred Kavli, a Norwegian-American physicist, entrepreneur, and philanthropist, who turned his lifelong fascination of science into a lasting legacy for recognizing scientific breakthroughs and for supporting basic research. The Kavli Prize involves cooperation among 3 partners. The Norwegian Academy of Science and Letters is administering the Kavli Prize together with the Norwegian Ministry of Higher Education and Research and the US-based Kavli Foundation. It is paramount that the choice of laureates is recognized globally. The Norwegian Academy of Science and Letters appoints the Kavli Prize committees on the basis of nominations received by leading international academies and other equivalent organizations. Each prize committee consists of 5 members who are all world-class scientists. The prize committees are tasked with reviewing and discussing the nominations received through an open international call. Unanimously, they provide a recommendation to the board of the Norwegian Academy of Science and Letters. Let me take this opportunity to say a big thank you to the Kavli Prize Astrophysics Committee led by Professor Viggo Hansteen. You've done a great job in identifying these 2 outstanding scientists. We all deeply appreciate your efforts. This week, the Kavli Prize Week 2024, we will celebrate science and the scientists behind the science. The Kavli Prize Week includes symposiums, lectures, the award ceremony, banquets in Oslo and Trondheim, and interviews with the laureates. But here and now, we look forward to the 2024 laureate lectures in astrophysics. Please let me introduce Professor Viggo Hansteen, Chair of the Kavli Prize Astrophysics Committee. He will guide us through this session today. Viggo, the floor is yours.
Thank you. I'd like to say, to start, that the universe is a really large place. Even our little corner of it, the Milky Way, has of order 200 billion stars, and it's not even that crowded. In the solar system's vicinity, the typical distance between stars is measured in terms of parsecs, which is the distance light travels in 3-something years. That's not a small distance. In our solar system, the distance to the sun is of order 8 minutes, and the distance to the edge of the solar system can be measured in hours. So with 8,000 hours in a year, more or less, the distance to the nearest star is 3,000 times bigger, further away than the size of the solar system, or 30,000 times the distance to the sun. So measuring the distance to stars was an extremely difficult task. And it took many, many years of humans looking at the sky before they figured out to do it. In fact, it wasn't until 1832, or maybe 1838, depending on how you count, that one was able to measure the distance to stars. And that was done by measuring the position of a star, maybe in the spring and in the fall, and then seeing how much a star changed position relative to back in the stars that lie around it. It's an extremely fine precision measurement, and that's how we define the distance of a star. So the stars are really, they're suns, they're far away, but are they like the sun? It took another 150 years before we could answer that question. So a planet orbiting a star will rock that star back and forth. So to discover a planet, if you can't see it directly, and believe me, you can't, all you need to do is measure how much a star jiggles. Now that sounds easy, but it's not. In fact, it took until 1995, by observing the back and forth motion of a few stars, and by the universe being kind enough to supply us with some stars that have big planets orbiting close to the star, to be able to find them. And it was done. But not without controversy. And it took another 4 or 5 years before one was concerned. And the reason for that is that the position of a star is not easy to measure, and there may be other effects that cause it to look like it's jiggling. But planets can cast a shadow. And that will cause the starlight to dim just a little bit. And it will dim in a regular cycle. So when that was determined, and in fact it was not least by Dave Charbonneau who discovered this, the debate was essentially over. The sun is not alone in having planetary systems. So after that, in roughly 2000, the next questions were one of statistics. How many? What kind of orbits? Where are they? What are they made of? Now, 25 years and several thousand exoplanets later, we know that the answers to some of these questions. In summary, there are a lot. And some large proportion are Earth-like. But there's a Norwegian expression that says, mye vil ha mer, or to put it another way in English, much wants more. And this is where our prize winners come in. They've charted a course for asking the questions that maybe motivates more than anything else. Can any of the millions, maybe billions of Earth-like planets that exist in our galaxy have the conditions that support life? And if so, what kind of life? In short, are we alone? So, to start, David Charbonneau is the Fred Kavli Professor of Astrophysics at Harvard University. He led the discovery of the team of the first transit of the giant exoplanet HD 209458b. He's used the Hubble Space Telescope to directly determine chemical composition of the atmosphere around the giant planet, and the Spitzer Space Telescope to make the first detection of the thermal infrared emission from an exoplanet. He's a member of the Kepler mission. Currently, he's actively involved in the Transiting Exoplanet Survey Satellite mission and the James Webb Space Telescope, and he's doing James Webb Telescope observations, as well as leading the innovative M-Earth project, aiming to detect rocky planets. And, not least, he's the co-recipient of the Kavli Prize in Astrophysics this year. So please.
All right. Good morning. Yeah. Okay. So today what I'd really like to do is talk to you about a certain kind of planet, which are called terrestrial planets. Okay, thank you. And what are terrestrial planets? Okay, well, we've got 4 of them in the solar system. Here they are. Okay, so we've got Mercury, Venus, Earth, and Mars, drawn to scale. So these are planets that are made with cores of iron. They've got a mantle of rock, of magnesium silicate, and they've got no atmosphere or a relatively thin, what we call secondary atmosphere. And we're fascinated by these worlds because, of course, we live on one of them. And often we refer to the search for and the study of terrestrial planets as being the holy grail of astrophysics, particularly when it comes to establishing that there might be life on another such world. And the reason we use the expression holy grail is because it reminds us of a quest. It's a great quest. It's a unifying idea for a transcendent object, something that takes us beyond the mundane, the everyday, the here and now, and connects us to something profound about the universe that we live in. Could there be life, possibly even intelligent life, that we might one day come into contact with? The flaw in the analogy of the Holy Grail is that the Holy Grail, remember, was unobtainable. But actually, we've made enormous progress in terms of learning about terrestrial planets. And so what I want to do today is actually focus not on the future and all the great things we're going to build and do, which is something I spend a lot of time thinking about, and many of you do as well, and we're very excited about that future. But I want to actually talk about what we've currently learned about such terrestrial planets orbiting other stars. Okay, here is the big opportunity that has recently opened up. We have this incredible new powerful observatory, the NASA James Webb Space Telescope, much bigger and sensitive to infrared wavelengths and pushing our ability to study potentially the atmospheres of terrestrial exoplanets much deeper than Hubble could. And then we hope, in the very near future, to have several very large ground-based telescopes. And here I'm showing you the Giant Magellan Telescope, which is a project that I'm part of. And the question is, can we use these observatories to actually study molecules in the atmosphere of not a gas giant planet, but a rocky planet orbiting another star? And the method we're going to use is this idea here. The planet goes in front of the star. Some of the light is going to pass through the atmosphere of the planet. We study that light, and imprinted on the starlight are the telltale fingerprints of the atoms and molecules that are present in the atmosphere of that world. So we've done the math, and the answer is that yes, this works. JWST can do this. These large ground-based telescopes can do this, but only for stars that have two properties. They have to be within 15 parsecs, and they have to be small. All right, so what's 15 parsecs? So as you heard, the Milky Way galaxy has roughly 200 billion stars. It's vast. If I took the entire galaxy and I shrank it down to the size of the Earth, okay? Here I'm talking about studying stars that would happen to fall within the city limits of Oslo, okay? So we're talking about our very, very closest neighbors, and because they're close to us, they're relatively bright, and we finally have enough light from the stars and the planets to study them. The stars also have to be small, roughly a third or smaller than the size of the sun, and the idea is if I make the stars small, then the light from the planet, the size of the planet, relative to that overwhelmingly bright star, is now makes the study of the atmosphere accessible. Okay, so a brief tutorial on stellar astrophysics. Stars come in all shapes and sizes. This is the star that we happen to orbit. It's a sun-like star. It's very sun-like. Okay, and here it is drawn to scale with the Earth. Okay, so the Earth is really, really small. But most stars, and you know, in high school I was told we orbit an average star, and that was a big lie, right? We actually orbit a very, very peculiar star. It's much more massive and larger than most stars in the galaxy. Most stars in the galaxy are these small pipsqueak stars that astronomers call M-dwarfs. But M-dwarfs themselves come in an enormous range of sizes. They range from about 8% to 60% the mass and the size of the sun. But remember, I said the stars have to be smaller than a third the size of the sun. And so we need to actually cut out most of them and just focus on all of the stars in this size group that happen to fall within 15 parsecs. Now, entirely by coincidence, that is the point at which there is a profound change in the physics of the interior of the star. So my motivation was opportunistic. I want to go and look for planets, and I realized the star has to be small. But that's the point at which the interior of the star becomes fully convective. So our star has two zones, a convective zone and a radiative zone. And the interface between those zones, we think, is what creates the magnetic field of the sun, which plays such an important role in what? Controlling our atmosphere and the loss or retention of atmospheres of planets orbiting the sun. Now we have stars that are going to be profoundly different, and so their magnetic activity, their X-ray emission, their ultraviolet emission, the particles they shoot off might be profoundly different, and that itself might influence the very atmospheres that we're hoping to study. Let me introduce Jen Winters. So Jen Winters was a postdoc in my group. We worked together for 6 years, and Jen outlined this sample. Okay, so she wrote down the 15 parsec sample. All stars, volume complete, every single star that meets this criterion within 15 parsecs. She counted them up. There's 413 such stars. There's not going to be better, closer stars that someone's going to find 100 years from now. So we have to find the planets around these stars, and those forever and ever, next year and 100 years from now, will always be the best targets. We have 3 goals in this survey. Okay? One is we want to measure how common these terrestrial planets are around this kind of star, which happens to make up about 70% of all the stars in the galaxy. Measure the rate of occurrence of Jupiter-like planets out where Jupiter is, so far away from the star in much colder environments. And characterize the magnetic activity and how long the star remains magnetically active, because of that idea I mentioned earlier. And to do this, we're going to use 3 facilities, and I'm going to describe these to you. There's the MERTH project, the TESS mission, and high-resolution spectrographs on 1.5-meter telescopes. And if you're not an astronomer, you might think, oh, that sounds really big. But if you're an astronomer, you think, do they still make telescopes that small? And they do. And actually, many of you have access to them through your institutions. And my point here is the tremendous science that you can do with these relatively small telescopes. Typically, these were often built in the 60s. Okay, here's the MERTH project. So MERTH is 8 telescopes that are each only 40 centimeters in size, so the mirror is about this big. And there's 8 of them in Arizona, and there's 8 of them in Chile, because we want to see stars in both the northern and southern hemispheres. And if I have to summarize MERTH in one slide, it would be this. Now, just like Norway is a place that is 4.5 billion years in the making, and then people come and do a 24-hour nutshell tour of Norway, and they expect to learn everything there is to know about Norway, MERTH is a project that's 15 years in the making, and I'm going to tell you about it in one slide. So please understand that there's a lot more going on here. But basically, we have 16 telescopes, and the trick is we need to look at all of these nearby stars, one after the other, throughout the course of night after night after night, and repeat a measurement of any given star every 20 minutes, because it takes roughly an hour for a planet to pass in front of a star. We don't know which stars are going to show such signals, and we don't want to miss the planetary transits. Okay? So if you watch MERTH in action, you'll see this swirling of these 16 telescopes as they're constantly hunting and pecking. But in very real time, they'll notice that a star is fainter by maybe a part in 1,000 than it had been for the previous 200 days. And suddenly, the telescope will stop what it's doing and will keep studying that individual star to catch the end of this planetary event. This is the TESS project, also going to be very important for the study that I'm outlining. Okay, TESS is 4 very small telescopes. Okay? You can see the telescopes there. Those are each basically camera lenses. They're only about this big. But it's in a heck of a location, which is that it's in space. And here's how TESS surveys the sky, okay? So the 4 camera lenses are pointed like this, so that in a single snapshot, okay, you can take an image of a swath of the sky going from the pole all the way down to the equator. And then TESS makes observations of all the stars that fall within that field of view for about 28 days, and then it moves on to the adjacent orange slice, and it does that over the course of a year, and then it flips over and it does it in the other hemisphere, and it's been doing this for about 5 years now. Okay, so we've gone back and revisited a number of stars several times. So we get exquisite photometry from both the ground with MERTH and from space with the TESS observatory. And then the last piece of the puzzle is spectroscopy. Okay, so we need to take spectra of all of our stars. And so you might ask, haven't people done this? I mean, these are literally the very closest stars to us. Okay? And people have been doing spectroscopy of nearby stars for more than a century. Well, Jen Winters went and scoured the literature, and here's what she found. So these are all of her stars displayed on the celestial hemisphere, on the celestial sphere. The ones that have a nice high-resolution, high-quality spectrum are shown in blue. The one that have a low resolution, inadequate spectrum are shown in green. And in red, as far as we could tell, nobody had ever taken a single spectrum ever of that star, even though some of those stars were less than 10 parsecs away. Shocking. And so what Jen set out to do was to use these small 1.5-meter telescopes in Arizona and in Chile, and to monitor these stars over the course of about 6 years. Why monitor them? Because we want to see if they're changing, if they're accelerating due to the influence of an orbiting companion. Okay, so those are the facilities for the project. Okay, we've got the MERTH project, the test mission, and the high-resolution spectrographs. Now, let's get to the actual science questions. So the first question, right? How common are these terrestrial worlds? And not just how common are they, but what is their relative distribution? Are they mostly small? Are they mostly big? Okay, so before you go out and look at other stars, here's what you know about the histogram of the distribution of terrestrial planets. I made this myself. And you can see that we have 2 Earth-sized planets in our solar system. We have 1 Mars-sized planet, and we have 1 Mercury-sized planet. And so here's the distribution they get, the number as a function of the size. Okay, but maybe physics doesn't do that. That's just what happened due to stochastic effects in our own solar system. Maybe the actual distribution looks like this. It could be due to dynamical effects that all the planets end up combining. In the solar system, they didn't, but you stick all the rock together and you get 1 big rocky planet. And if so, then you might expect the distribution to look like that, peaking at something that's about 1.5 times the size of the Earth. Or maybe it's like this. It's small planets all the way down, okay? And nature, I mean, the things start out as small specks of dust, and they coagulate and they stick together under gravity to form bigger planets, but you might end up with a distribution in any given system where the smaller planets always outnumber the bigger planets. Measuring this would profoundly affect our understanding of the physics of formation of terrestrial planets. This is a really important thing to do, and the solar system is inadequate. Okay, so just before the study that I'm outlining here, Courtney Dressing and I had analyzed the data from the NASA Kepler mission, okay? And the Kepler mission studied an enormous number of stars, but they were mostly more massive stars. So they weren't the really small M-dwarfs that I'm talking about. They were intermediate in size between the sun and the low-mass stars. And what Dr. Dressing found was that actually Earth-sized planets are incredibly common, okay? So for all of the stars in the survey, and again, this is the most common kind of star in the galaxy, 1 in 2 stars has an Earth-sized planet, and 1 in 4 stars has an Earth-sized planet that is in the habitable zone, okay? That actually is at the right distance, the Goldilocks region, where it's not too hot and not too cold, where if there was a lot of water, it would be liquid on the planet. Christo Ment, who just finished his PhD in our group the year before, this year, so just a year and a half ago, Dr. Ment wanted to go and take Courtney's study and now go down to these very low-mass ones because those are the ones that we're going to be studying atmospherically, okay? And I want to show how challenging this is, all right? So here I'm showing the detection of transits in front of one of these stars, okay? So here's a transit. Here's a transit. These are different nights of data with the MERTH observatory. And you can see these tiny little signals on this vast ocean, and that ocean is stellar variability. There are spots, there are flares, the star is rotating, and it's changing its apparent brightness. And you have to correct for all of that and find these tiny little signals that are periodic on top of this vast ocean, this little boat out in your Norwegian fjord. Okay. If we want to know the intrinsic rate of occurrence, of course, it isn't enough to find planets, but you have to know how many you would have found if all such stars had planets. And so the heart of what Christo did was to take every single star, okay, so not quite 413, but nearly all of them, some of them were not observed by TESS yet, and ask for every single star, if I inject a planet of a different size, okay, here I'm changing the size of the planet, and a different orbital period, okay, how many would you have found? And so if the planet is big enough, I find 100%. I wouldn't miss such a planet. I would definitely know if it transits. And then as I move towards smaller planets, then my sensitivity falls off. If I put a planet that is the same temperature and size as the Earth around a typical star, and this is one anonymous but typical star in the survey, it's right here. Okay? So the point is that the data are good enough to find those planets, and they're actually good enough to find planets down to the size of Mars and or Mercury, depending on the star. Okay? So we have incredible sensitivity to these very, very small worlds, and we certainly would find the Earth-sized ones. Okay, so then Christo did his survey, and here's what he found. These are all the transiting terrestrial worlds that are in that sample. Okay? Now, these weren't new discoveries in themselves. Christo had already found several of them, and several others had already been found by Mirth and by Tess. So for example, here was an early Mirth discovery. That's a Tess discovery, and so on. There's another Mirth discovery. These were found by Tess. But he recovered them independently so that he had a nice, consistent sample. Okay? And here I'm showing what it looks like to discover some of these worlds, right? You see this stellar rumble, and then you see this transit as the planet goes in front of the star. Okay, now if I plop these down on that sensitivity plot that I showed you earlier, you can ask, did I find planets in the places that I expected to? All right, so here are those 7 planets drawn as stars. Okay, here's their radius relative to the size of the Earth. Okay, when Sarah and I started in this field, the idea that you would stop your radius diagram at 2 Earth radii was ludicrous, right? The only planets we could find were 15 or 10 times the size of the Earth. Here we can draw all the way down to 0.4, 0.5 times the size of the Earth. These are the 7 worlds. And here I'm plotting not orbital period, but insolation. So how much energy from the central star per unit area, per unit time, does the planet receive relative to what the Earth receives? So it's a proxy for conditions, it's a proxy for temperature. Okay? And so you can see, you can find very, very strongly irradiated planets, 100 times as much energy as we get, down to about 4 times as much as the Earth. So here we're not looking quite at the habitable zone, but we're getting very close. Okay, very, very interesting. Now, if planets were uniformly distributed in size and in insolation, then I would have found them all across this plateau, right? I have perfect sensitivity there. I don't miss planets there. But I don't find a single one, right? So right away, you've learned something about the radius distribution of planets. Why are there no planets there? Where are the 1.8 and 2 Earth radius planets around these low-mass stars? They do not exist. Similarly, you can see that suddenly there's this big population at about 1 Earth radius, and then they seem to roll off, but they roll off too quickly. Here I'm 70% sensitive, and I have all these planets. Here I'm 50% sensitive. I would expect to have almost as many, but there's none. There's none on that contour. Why are there no planets here? So my point is, of course, without taking you through the full statistics, by looking at this plot, where did you find planets relative to where do you expect to find them? Then you learn about the underlying distribution in terms of the radii of worlds. And so if we reconstruct from those data what that distribution would look like, we get this plot here, okay? So the underlying color, the bright yellow, indicates the population of worlds that we infer from this study. And what we learn are 2 things, that for these low-mass M-dwarfs, okay, they also have at least 1 terrestrial world for every 2 stars, probably more, because we only go out to a certain orbital period, and the planet radius distribution is consistent with peaking at the size of the Earth. So Earth seems to be the most common size for terrestrial worlds. Okay, so those are the terrestrial worlds. Now the question is, are they really Earth-like? So are these the siblings of the Earth and Venus? Or are these different in some profound way? Yes, they're made of rock and iron, and yes, they have roughly the same temperature, but is there something about them that makes them truly alien? To understand that, we have to ask about the other planets in the system. and in particular the presence of Jupiter and Saturn-like analogs around these stars. And so here I want to highlight the thesis work of Emily Pass, who just defended her PhD a couple months ago. What Emily knows is that in our own solar system, Jupiter and Saturn did not stay put. So we now understand, and this is called the Nice model, because it was proposed, I believe, at a cafe in Nice, France, not because it's nice. And what Jupiter and Saturn did was, after they were formed, they moved, okay? And they first swooped in close to the sun, and then they backed off again. And what this did was to control, to regulate. Most of the mass in a disk that's forming planets exists far away from the star. Jupiter and Saturn are the gatekeepers, allowing that matter to enter or not enter down towards where the terrestrial planets are going to form. As Jupiter and Saturn migrated in, the feeling is that resulted in what we call the late heavy bombardment. When you look at the moon, you see all those craters. Mars has got lots of craters. All of this material came and bombarded in an epoch when these guys were moving. All of this material is gravitationally scattered in, and there's discussion that really that's where most of the oceans came from, was all that scattered cometary material. So this really affects the inventory of molecules that the Earth has, and profoundly affects how Earth-like these worlds are really going to be. So what Emily did was to gather data for all of those 413 stars, to look at all the spectra that Jen had been gathering, and to look very carefully to see if we saw the telltale wobble back and forth due to the presence of Jupiter and Saturn-like planets out at the snow line, out at these more distant regions. And Emily searched and searched, and she found not a single one around all of those stars. Sun-like stars, that's the most common architecture there is. There's plenty of Jupiters and Saturns out at Jupiter and Saturn distances. It isn't just a feature of the solar system. We know directly from studies that have been going on since the 1990s that we can see these Jupiter and Saturn analogs around sun-like stars. But low-mass stars don't make giant planets. So that means that these Earth-like planets are going to be very, very different in terms of how much water and how much volatiles they're actually going to have, and therefore their atmospheres and the presence of oceans may be profoundly different. And we need to keep this in mind as we set out to study their atmospheres. The last part of the study is to really get at the physics of these low-mass stars and to ask, what about the magnetic activity? Okay? So first I need to tell you about the sun. So the sun was born in a very tumultuous way, and it had all sorts of X-rays and ultraviolet light, and it spun rapidly, okay? And it absolutely bombarded the terrestrial planets of the solar system with all sorts of very high-energy photons and a wind due to the sun that would strip away our atmospheres. But it only did that for perhaps the first 50 million years. However, atmospheres are outgassed from the rock of the planet, and they're produced over timescales of several hundred million years. So it's okay if all of the particles and X-ray flux strikes the planet, and then later the atmosphere is outgassed after the star has calmed down, because then you get to keep your atmosphere. If that sequence of events is reversed, if planets first produce their atmospheres while the stars are still active, then that's going to be catastrophic for the retention of those planetary atmospheres, because the stellar activity will strip away the planetary atmosphere. Okay, so that's this idea right here. Okay, so we are constantly losing atmosphere, but we replenish it a little bit and we reach a nice balance. That needn't be true. I mean, look at Mercury. Okay, so here I want to show the thesis work of Dr. Elizabeth Newton. And what Dr. Newton did was to take all of the measurements that we've been making with MIRF for a decade and to ask, can she see how quickly these low-mass stars are spinning? And really the way you see that is the stars have spots, and as the spots rotate in and out of view, the star appears to change ever so slightly in brightness, and you can infer how long it takes for the star to spin on its own axis. The sun takes 25 days to spin once around. The wisdom at the time was that all low-mass stars spun very quickly. They spun maybe every 12 hours, okay, or every 1 day. But nobody had looked over very long timescales. And Mirth now had suddenly looked at some stars for a decade. And what Dr. Newton found was astounding. Most of these stars actually spin incredibly slowly, okay? So here we saw that there was all sorts of these low-mass stars that were spinning with rotation periods of 100 days, 130 days, incredibly slowly rotating stars, which means magnetically they're going to be probably very, very inactive. Whereas if you look at there seems to be this other population in this local volume of space that are spinning incredibly rapidly. They spin every 12 hours or so. Those are the ones that had been known before, and that's why people thought all of them were in this category. Now, here we're complete. Here we only make a detection about half the time. So there's most of the stars actually live up here. What's interesting is that there's really not much in the middle. Okay? So what does that mean? And here we draw on the physical picture outlined by Dr. Timothy Brown, okay, of the high altitude and Las Crumbres observatories, that these stars start out spinning very quickly, and then, maybe in the words of my southern wife's family would say, they have a come to Jesus moment. And they suddenly lose all their angular momentum. Now, really what's going on, we think, is probably the magnetic field realigns into a dipole, and it can couple strongly to the stellar wind, and it has a way to lose angular momentum. Okay, we think there's a physical picture there, but we're not sure. But that there's a sudden moment that's stochastic when they rapidly spin down, and the spin down happens very quickly. So that would explain this picture, right? They live in this reservoir of rapidly spinning stars, and then at some point, any one star suddenly spins down, and it does that very quickly, and it lands out in this place where it's almost lost all of its angular momentum. What does that mean for their activity? Okay, so here we know about their rotation period, but what does that mean in terms of their production of particles and X-rays and the things that might really affect their atmospheres? Here I'd like to show some plots from the work of Amber Medina, who finished her PhD here actually in her Harvard robes from a couple years ago. And Amber was fascinated she arrived interested in flares at Harvard. She was very interested in stellar flares. And here I'm going to show some beautiful data from the TESS mission. Okay? So here we're measuring the brightness of a star. This is one of these stars in the sample, as a function of time in days. These are days. Okay, so don't worry about the large number, but basically, 1 day, 2 days, and so on. And here you can see this beautiful sinusoid in the data. That's the rotation of the star. The star has spots, it's rotating, you're looking at one side, and the star gets a little bit brighter and fainter over time. Okay, so we can get the rotation period that way. Often we know that rotation period already from the Mirth data, but here you would clearly get it. But if you subtract that sinusoid, then on top of that, you see these events. You can see them here. There's one, these moments where the star suddenly gets really bright and then fades away again. Okay, those are the flares. Those are the actual stellar activity that we're very interested in constraining. And so for every single one of these stars, Dr. Medina was able to measure how frequently they flare, again, using that kind of injection and recovery methodology I described earlier. She could say, well, I would have found flares of a certain energy. I found this many. How often do they produce flares of that energy? And she found this very interesting dichotomy. Okay? So here I'm plotting the flare rate. The units don't really matter, but it's a logarithmic plot. Okay? And when stars spin slowly, so here's a rotation period of 1 day, they all flare frequently. They have enormous flares all the time, multiple giant flares per day. Okay? Much, 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 much more than the sun really probably ever had. Okay? But when the star, and then there's no stars in the middle, that's that gap I talked about in rotation period. There's simply no stars here. And then when the stars slow down to these rotation periods of 100 days or 130 days, they fall by, a factor of, this is not base 10, but they fall by a factor of about 7,000 down to here, okay? So the flare rate drops basically to 0, okay? So a tremendous change. Very, very interesting. And here I'm showing known planetary systems. So there's a star where we know that there's a transiting planet, but here's 3 other transiting planets that we found, and they all orbit these very, very inactive stars. But this picture tells you that those stars were not always the calm parents that they are now. Okay? Throughout much of the youth of the planet, the star was incredibly active. And what might that have done to the atmosphere? Okay. So here I'd like to show some other work from Dr. Pass's thesis. And basically what you can do, okay, is you can take the relative populations, okay, so you take this volume complete sample, and we know from other studies of galactic archaeology that basically these stars have been born continuously at a constant rate. New stars are being born in the galaxy for about the past 8 billion years. So the fraction of stars that I see that are now spinning quickly and active versus the ones that are inactive tells me the time at which this transition occurs as a function of the mass of the star. You see? I can say, well, I see this many that are active and this many inactive, and I assume they're born uniformly across 8 billion years, and I can figure out the moment at which they typically spin down. And that's this plot here. That's what Emily deduced, okay? So here she's plotting the active fraction as a function of mass, okay? So we're looking at stars that are no more massive than 30% that of the sun, but there's some that are 25%, 10%, okay? And here is the implied spin down time that you would get from that calculation. So stars that are 30% the mass of the sun, they are active for about 1.2 billion years, far, far longer than the sun ever was. And then as you go down in mass, that activity timescale gets longer and longer, reaching, about 4.5 billion years by the time you get down to stars that are 10% the mass of the sun. So this active lifetime is much, much longer than the epoch over which physics tells us that the planetary atmospheres were produced. So do these planets actually retain their atmospheres? Are they going to be Earth-like? Or are they going to be denuded chunks of rock, okay, these fossils of once Earth-like worlds? Well, we are now making progress on that question. We can actually directly look for these atmospheres. And here's the first such study by Laura Kreidberg. Laura Kreidberg was a postdoc with me at the Center for Astrophysics. Okay, she's now the director of Max Planck Institute. And what Laura did is she came and she said, David, I want to propose for 100 hours of Spitzer time. And I confess, I said, that sounds like a lot. But she is very persuasive in her proposals. And what she was able to do was take one planetary system and take the Spitzer Infrared Observatory and simply monitor the brightness, okay, monitor the brightness of the planet as it went around and around and around its star. When the planet is about to pass behind the star, you're looking at the day side of the planet, okay? That's the side of the planet that receives the light from the star. It goes behind the star, and then it comes back into view. So that's this part here, right? Here you're seeing a lot of light from the planet, and then it suddenly disappears because the star is blocking that light, and then it reappears. So we call that a secondary eclipse. Then as that planet rotates around, you look at the night side of the planet. Now I'm looking at night side, night side, night side, night side, sort of quarter moon, and now back to day side again. So basically you can measure, as the planet rotates around, how much energy is being released, i.e. how hot is the day side compared to the night side. If the planet has an atmosphere, it can move the heated gas from the day side to the night side. When the sun sets here in Oslo, it does not drop to 0 Kelvin, okay? There's only a very modest change in temperature, and that's because we have this wonderful atmosphere. What Laura found was for this particular world, it did drop to 0 Kelvin, okay? So this planet has no ability to redistribute energy from the day side to the night side. This is very compelling argument that this planet has no atmosphere. Now, this is not so surprising. This is an incredibly irradiated world, okay? But now as we march down to colder and colder planets, are we going to see a shoreline? Are we going to see a moment at which they suddenly do have their atmospheres? Or have they lost those atmospheres due to the irradiation of the central star? And I wrote Laura, and she very kindly shared the state of the field, okay? And so here are other worlds that are being studied as we go down in temperature. If they fall on this line or near this line, that means that they are as bright as they could possibly be on their day side, meaning they have no atmosphere. If they fall below that line, it means that they're fainter than their day side could be, and so they probably do have some atmosphere. And so here we see that these planets have also probably all lost their atmospheres. Intriguingly, this one world, TRAPPIST-1c, is slightly below the line. It's the coldest one that's been published so far. But there's all sorts of worlds right in here that are going to be the subject of an enormous allocation of time through NASA over the next few years. And so I would say really getting at this question is probably, in my view, the most exciting question in exoplanet atmospheres that will be addressed really in the next year or two. Okay. All right, so to summarize, when we think about the terrestrial planets of low-mass stars, okay, here are the four major takeaways. One, they're incredibly common, okay, at least one for every 2 stars. 2, they're very alien in that they grew up in a system with no Jovians near the snow line. And 3, they're alien on another axis, which is that they experience extremely high levels of X-ray and particle fluxes for billions of years, much longer than we think the timescale over which they produce their atmospheres. Finally, we now know, and this is very recent stuff, that a handful of the hottest planets have indeed lost their atmospheres. But these are not yet the ones where that's so surprising. And in the next year or two, we're going to move towards studying worlds which are much more temperate, where we really will learn about these planets' ability to retain their atmospheres and indeed whether they might actually be Earth-like examples out there. Okay, thank you.
Thank you. All right. How do we do this? I suggest that we save up the questions until Sara is finished.
Sounds good.
Makes sense to you?
Sure.
Okay, let's do that.
Okay.
And moving on here, thank you very much. We have one more winner. That is Sara Seager. She's the class of 1941 professor of planetary science, professor of aeronautics and astronautics, and of physics at the Massachusetts Institute of Technology. She pioneered the theoretical study of planetary atmospheres. She's made outstanding contributions to our understanding of planets with masses below that of Neptune and provided new concepts for our understanding of the habitable zone. And this established the importance of a variety of biomarkers. She was among the first to recognize the importance of a star shade as a free-flying external occulter to block the light of a parental star and allow the detection and characterization of a second Earth around a solar analog. And she's a co-recipient of this year's Kavli Prize in Astrophysics. So please take this aid.
This story begins billions of years ago, when a simple single-celled life form, cyanobacteria, figured out something very clever. I don't know about you, but I tend to think of the bacteria, think of like the slime in your fridge, not too clever. But in figuring out how to harness energy from our environment, namely photosynthesis, this life form generated a waste product, oxygen gas. And oxygen, it took a while to react with its environment and eventually, over 1 billion years or more, fill our atmosphere. So today, 20% by volume of our atmosphere is oxygen. Without molecular oxygen, we humans couldn't survive. But it's such a reactive gas, it shouldn't be in our atmosphere. It should be reacted away. So it has to be continually produced. Are you with me? Because if there is an intelligent civilization on a planet orbiting a nearby star, and they have the kind of telescopes we're hoping to build, and they see oxygen, they'll be highly suspicious there's life on our planet. We all know they're probably fighting over data analysis and signal attribution, but nonetheless, it turns out that 100 years ago, the renowned astronomer James Jeans first put this idea out there, actually. It's kind of like a small paragraph in a textbook on astronomy. And we've held on to this idea ever since, that we can find a gas that doesn't belong, that's way out of equilibrium with its environment, and it might be a sign of life. And that's the hope we have in astronomy, and the rest of the world and other non-exoplanet scientists are counting on us. So that's what I'm going to tell you about today. I'm going to update you where our thinking is on it. And the reason the hype is so strong right now is because of the new James Webb Space Telescope, arguably our first ever opportunity to carry out this task. So we all know what a transiting planet is, and thanks to the previous talk, you've had a bit of background. But I'm going to give you just like the most miniest tutorial on transmission spectroscopy. It's one of the reasons why we're here today celebrating the prize in astrophysics for exoplanets. But also, I know some of you aren't familiar with this. So just bear with me for a couple of minutes. Showing you here real data from the James Webb Space Telescope. It's this transit of a star. You can see the artist's conception on the top. Fortuitously aligned, the planet goes in front of the star, as seen from our viewpoint. And what we do observe is the bottom plot. It is the relative brightness of the star as a function of time. And you all see this drop in brightness, right? Okay, so it's a characteristic drop, and depending on the planet size and compared to the star, and the distance from the star, it shapes that curve. But what I want you to pay attention to just for a moment, you all remember pi r squared is the area of the planet and pi r squared area of the star. This drop in brightness is a ratio of the two. So the artist here made in a very exaggerated atmosphere in light gray. Do you all see that? So what it's conveying to you is if there's a planet atmosphere, the planet looks a tiny bit bigger due to the atmosphere. But we have to take this a step further because the way we want to think about it is at some wavelengths, the atmosphere is transparent. It doesn't have an effect. And so during transit, the drop in brightness will be that dark part of the planet compared to the whole star. But at wavelengths where the atmosphere is strongly absorbing, the planet looks a little bit bigger because now you're adding that gray annulus. Are you with me? Okay, we're now going to try it. So I have this data. And what you're looking at here is a transit taken with the James Webb Space Telescope of WASP 39b. And the black is the best fit to the transit. And the colors are different wavelengths. So the planet itself is blocking out some amount of starlight. And this atmosphere, yeah, you're seeing the atmosphere at different wavelengths. And the wavelength is indicated in microns in the top right. So each and every one of you, pay attention. Your job is to try to see by eye if the planet's a tiny bit bigger at a certain wavelength. So if the points are dropping beneath this best fit curve. If you didn't understand anything I said, you can still enjoy this part of the talk, okay? Anyone, have you seen it yet? Because you've got to simultaneously watch the drop and look at the top right. Okay, next time it comes around, someone just shout out what number you see, what wavelength. Oh, did you see it? Okay. 4.4, okay, we have a number 4 point, we'll take 4.37, okay, that's good. Right, well, let us take a moment and let this land. By eye, you have seen evidence of an exoplanet atmosphere. So we plotted a little differently to make sense of it, and now you're seeing the amount of light blocked as a function of wavelength, and the wavelength of light is in microns again. So you can check your answer here, see if you got it right. It looks like it's between 4 and 4.5, let's say around 4.3. And what you're seeing here is these points. We used to say before, like if you want to believe you've seen an exoplanet atmosphere, you just have to agree that the points, the real data, the white points with error bars, are different from a straight line. Because the planet is looking a tiny bit bigger at wavelengths where the atmosphere is strongly absorbing. And this wavelength, this gas, turns out to be carbon dioxide. We all know it's a strong absorber because on Earth we're worried about increasing carbon dioxide as a greenhouse gas. On this planet, it's not the dominant form of carbon, it's just a very strong absorber. I have another broader wavelength plot for you to enjoy and just appreciate that. Well, back in the early days I'll just tell you a very brief story. This now goes back to the last year of the last century, 1999. I was a newly minted postdoc, PhD, starting my postdoc at the Institute for Advanced Study in Princeton. There were about 30 exoplanets. They hired me because of my work in cosmology. Nobody knew what to do with someone working on exoplanets in those early days. So it turns out, if you're not great at small talk, and a lot of physicists are not, a good question to ask someone is, what's the next big thing? So everybody was asking me, what's the next big thing? I knew the next big thing was going to be a transit any day because we had the probability to transit we knew was 10% for planets close to the star. We had about 7 of them already. Not that the 10th one would, show a transit, but there was a chance the more we found. I had spent my summer finishing my thesis and pressing a colleague, Dave Latham, to give up, share some of his rate of velocity candidates, which he ultimately did with Dave. That led to the transit. So I knew it was going to happen anytime. So I started working on this concept I called transmission spectroscopy. Working along. One November weekend, I get an email from Dave about his discovery. Then I dropped everything to work on this paper, get the job done, get it out there, laying down some ideas for transmission spectroscopy, which Dave then later picked up and used the Hubble Space Telescope, and the rest is history. Well, being a postdoc, the next step is looking for a faculty job if one is going to stay in academia. Despite having written about this in advance, having the discovery so soon after, by what I had suggested to look for, I could not get a job. People were, kind of impressed, but not super impressed. Mostly it was a thought that, this is what people said, it is a one object, one method success. Because you need a bright host star to kind of backlight, and people thought there wouldn't be many transiting planets, the geometry has to be just so, not enough bright stars, people thought the field would dead end. In one esteemed university that I shall not name, interviewing for a job, someone sat me down, just said, there will never be many transiting planets. But we know there's thousands of planets, so many atmospheres have been observed, perhaps as many as 1/3 of all astronomers are working on exoplanets in some way, and we're really excited to share the continuing growth of the field. So now I'll move on to the second part of my talk, and we heard from Dave already, the transmission spectroscopy method, it cannot reach down to Earth-Sun twins. Remember the exaggerated picture of the atmosphere against the backdrop of the star? That doesn't work because the atmosphere is super tiny, like the skin of an onion on an onion compared to our whole sun's area. It's out of reach right now. I put some numbers for you. So we're not going to be doing that. And as my co-recipient mentioned, actually, I'm not going to go over this. If I could assign homework, it would be working out the math for that problem. It's relatively straightforward. I know there's students of different ages here, even the one in middle school. I don't know if you learned pi r squared yet, area of a circle, or how to find out the area of an annulus, but yeah, if I could assign homework, okay, you're probably on vacation. But you essentially just work out the math for the annulus, but then you have to ask yourself, how do we assign like a physical number to the height of the atmosphere? We use something called scale height, which is like an E-folding factor for how pressure drops off, and we can estimate this whole thing by using the ideal gas law and hydrostatic equilibrium. So that's for your notes. And we already heard about the small star opportunity, meaning that we can use smaller stars and make this work. So I'm going to talk about this middle category called sub-Neptune-sized planets. These planets are in between the size of Earth and Neptune, where Neptune is 4 times the size of Earth. And they're kind of an interesting type of planet, but the numbers work out and we can study their atmospheres. So I'm going to tell you a bit about this because it is a bit of, it's like a current problem, something we're trying to solve. Now, I'm going to give you a little thought experiment here because these planets are intermediate in size between Earth and Neptune. They appear to be incredibly common, perhaps the most common planets in our galaxy, but we don't know what they're made of, and we don't know how they formed or why they're even existing. So I'm going to give you a thought experiment. Imagine that I have 3 planetary materials, like a rock and iron mixed together. I have some water, and I have some hydrogen and helium. And I give you a box. You hold this box, it's so heavy, like it almost falls to the ground. Which of those 3 materials do you think it might be? It's this rock iron because it's so dense. Now imagine I give you a box, you don't know what's inside, and it floats away. That has to be the hydrogen-helium mixture that's lighter than air. But what if I gave you a box that's so intermediate? Can't open it. Actually, it's not going to be water. It's a mixture, but you don't know a mixture of how much. It could be a lot of rock with a bunch of hydrogen. It could be water, it could be a mixture, and I just tried to convey to you very briefly the problem we're facing, a problem of ambiguity. Given a measured mass and a measured size, we can get the density of a planet, But if it happens to fall in this very average range, it's nearly impossible for us to assign it a value. Now, we came to this realization many years ago. I'm very cheery today, of course, but it was super depressing and crushing. Because imagine you can never, it's very hard to say what is a planet made of, one of the most basic properties of a planet at all. But we came up with ways to, well, we thought elegantly anyway, it's a bit clunky, constrain every possibility for it. And so I gave you a few N members here. These sub-Neptunes could be a mini Neptune, truly a smaller version of Neptune with some water and a rocky core and a hydrogen-helium envelope. They could be this fictional water world we're hoping exists, like a scaled-up version of one of Jupiter's icy moons. Or it could be a gas dwarf, a rocky world with hydrogen-helium around it. So anyone want to guess which one? Okay, no, don't guess. Honestly, it turned out to be something, we think, that we hadn't anticipated, actually. It turned out to be something very in between, that it's an envelope, not of pure hydrogen helium, but it appears one to be mixed of hydrogen, water, and methane, all mixed together. So it's not like oil and water that stay separate. It's a mixture of things that mix together, making this big envelope, perhaps 10% of the total mass, at least of this one planet I've mentioned here. And then this rocky iron core, or not even a core, 90% of the total mass of the planet, turns out to be, because it's overlaid by this envelope that acts like a blanket and like a greenhouse, and adding high pressure, that this inside ends up having a deep mantle ocean, like a mantle, like liquid lava deep. And the clues as to why we thought this might happen was, well, first of all, we were all really holding out for this water world. And the observations of this planet, some of these Neptunes, this is all very sketchy and very frontiers, but they appear to have methane but no ammonia. The picture might change later. But if you have a hydrogen atmosphere, we're expecting a lot of the elements to be in their most hydrogenated form. So if you have methane, you should have ammonia, NH3CH4. But it turns out ammonia is incredibly soluble in water. It's like many orders of magnitude more soluble than methane. Therefore, if you have missing ammonia but you have methane, we want to assume there's a water ocean. And that would be really exciting. But it turns out that ammonia and nitrogen compounds also dissolve in magma. And so in finding a planet atmosphere that appears not to have ammonia, it's still ambiguous. It could be the water ocean or it could be magma. Anyway, I'm not sure if this part of my talk was as clear as I wanted it to be, but just to say exoplanets are so diverse. We're trying to embrace this diversity when we want to think of planets that might host life. We were hoping these mini Neptunes, or these sub-Neptune-sized planets, could be planets that might be able to host life because we love the water world idea. But the community's leaning toward the few we have so far atmosphere measurements of, that they're not going to be water worlds. They're going to have this weird hot rock liquid, not good for life. And that they're just a bit too hot. We need to find planets further from the star if they're going to be these sub-Neptune size with the hot heating atmospheres. Okay, so I wanted to just give you like the tiniest bit on atmospheres, but I'll let you read this slide if you're in the field. If you're not, I'll explain it to you in a more simple way. If you go back, dial your head back to algebra, if you have a system with 5 equations and 5 unknowns, you can solve it. And typically speaking, you would write down these equations, you'd have a matrix, you would invert it, and you would get your physical parameters. In this case, our equations are ones of the planetary atmosphere, like conservation of energy, energy transport. These are physics equations and chemistry. But our problem is that these equations are very nonlinear. So we can't just write them all down and invert a giant matrix. We have to use a class of an umbrella term we call inverse methods. Instead of inverting the matrix, we have a method, we call it atmosphere retrieval. We really just sort of flood, we could call it like a million model approach, where we generate millions or trillions of atmosphere models. We ask which fit the data, and then whichever ones fit the data could be the true underlying physics and chemistry of the atmosphere. Typically, we have to be clever about how we march through parameter space. And this means we have to heavily parameterize our models and get away from the real physics. We ended up in a bit of a mess right now in this field, and I was just going to try to highlight a bit for you. It's like having the 5 equations, or it's like setting up your problem, but our boundary conditions are unknown, and our coefficients are also not extremely well known. We have a lot of unknown issues. So I did try to make a graphic to explain this to you because it's super important in the search for life and the search for understanding planets today. So on the left, you see the James Webb Space Telescope illustration. We take observations, and most of you would be familiar with the second step on the left, that we would do our data analysis and assign error bars, right? There's an uncertainty to every measurement we make. But we have this added problem in the middle here. Because of the atmospheres and the density of the planet are ambiguous, we'd like to be able to not just say, hey, there's carbon dioxide or there's water vapor. We want to tell you how much there is. But because of this ambiguity, the planet, atmosphere, the interior, like, is all averaged together. There's a range of options. But how do we accurately and precisely give you those range of options? That's these inverse methods I tried to explain briefly to you. But do you know those also have their own uncertainties, which we haven't really quantified well? Because in these, for the people in the field, in these forward models, we're usually using Gaussian noise. We've overparameterized, oversimplified the models. And right now we're just struggling to understand how to assign those uncertainties so we can give a really decent representative of how much of which gas is in the atmosphere. And we have even seen some problems where people have different data of the same planet, but they lead to different planet archetypes. One claiming it's a water world, one claiming it's this other type of planet I told you with the mixed envelope and the magma surface. So we're trying to sort all of that out, but I wanted to give you a glimpse into where we are now and some of the problems we're facing. So let us say we have solved these problems. We can tell you, not super accurately, but we can tell you what's in a planet atmosphere. Let's say we assume that, and now we're ready to move on to think about what signs of life to look for. Well, Earth has only had significant oxygen for the past billion years, although the cyanobacteria and now plants and other photosynthetic life have been generating oxygen for a long time. We could ask ourselves what other gases might be produced by life on an exoplanet. Well, it turns out it's not just oxygen, but life on Earth actually makes thousands of gases. The smell in the forest, the mold in your fridge, your compost. But interestingly, I uncovered this factoid that every gas in Earth's atmosphere to the part per trillion level, with the exception of the noble gases. So every gas to the part per trillion level is made by life. Even ozone is produced inside some cells. Now, they largely have a dominant production that is not associated with life. But it's amazing how broad Earth life is, actually. There's about, so just for numbers, on our planet Earth, if you want to think about every molecule that can be in gas form at Earth's temperature and pressure, it's like 14,000 molecules. A large majority of those are halogenated, but about a quarter of them are made by life on Earth. So my team has spent literally more than a decade organizing all these molecules, generating databases, generating a framework to sort through what could be good biosignatures on another planet. And my favorite out of all of these, hands down, is a gas called phosphine. How many of you have heard of phosphine? Right, you've all heard of phosphorus. P is an element essential for all life on Earth. But on Earth, we have very little hydrogen. We have mostly oxygen. So phosphorus naturally goes as a phosphate. Also, the temperatures and pressures are very unfavorable for phosphine. It can't exist naturally. But we humans make it as a pesticide, as an insecticide. It's associated with life in oxygen-free environments. Honestly, it checks all of my favorite boxes for what makes a good biosignature gas. It has spectral features that are not present by dominant gases in the background atmosphere. So I've sort of led you up to where we are now. We have an established method to observe atmospheres using transmission spectra. There are some known rocky planets in the habitable zone of the host star. I glossed over it, we have a list of potential biosignature gases. So we're in good shape for this whole search for signs of life beyond Earth. We're in a good position, right? Well, we actually have a little bit of a prelude to our future of exoplanet biosignature gases, and it's not pretty. And this, some of you have heard of phosphine on Venus. I was working on phosphine as my favorite biosignature gas. My team had written a few papers about exoplanets and Earth, like where phosphine exists on Earth. And we learned about a team across the ocean led by Professor Jane Greaves, also working on phosphine as a sign of life. And she went out on a limb and wanted to search for signs of life on Venus. And she had found phosphine in the literature as this unique gas. And it also has a transition. It's ground to first excited rotational state at millimeter wavelengths, accessible by radio astronomy, where she's an expert. So someone connected our two teams, and she invited us to join. And I first saw the original data from the JCMT, and yeah, I was very confident this would go away. It just was not great, but we joined her team, we proposed to ALMA, we got more data. We presented it to the world in September 2020. We reported a detection of a small amount of phosphine gas on Venus, one that couldn't be explained by abiotic processes like volcanoes or lightning or meteoritic delivery or whatever, 100 pages worth of known chemistry. And what do you think the reaction was? It was immediately attacked, like then and throughout the last couple of years, at every level. And I want to just review this with you to be thinking about the future of exoplanets. So the first question, is the signal real? I mean, that's really the most important question. People analyzed the data, did not recover the signal on the whole. Some people did recover the signal with our JCMT data. But typically, we're going to be looking for tiny signals. And it's going to be, likely noisy data. We'll do our best, but it's definitely a challenge to pull out a small signal. Let's assume the signal is real. The next question is the molecule correctly identified? Out in radio wavelengths, just with rotational lines, the signals are pretty separated. Usually you don't have overlapping lines. You'd like to find more than one line or group of lines per molecule. In this case, only one was accessible. And it turns out there is one overlapping line of sulfur dioxide, a common molecule on Venus. It would have to be there in much larger quantities than it normally is for this line to be sulfur dioxide. Well, let's assume the first two are real. Then we get to the key question. Is the molecule produced some way other than by life? And with phosphine, we never said there's life on Venus. We just said there's room for life on Venus if we rule out all other possibilities. Oddly enough, Pioneer Venus, that went into the atmosphere of Venus nearly 4 decades ago, also saw signs of phosphine. All right, so we couldn't really, just to summarize, Venus. We can't necessarily prove there's no other way to make phosphine. We can argue as logically as we want based on everything we know, and we don't know all the phosphine chemistry. But bigger picture, it's hard to make phosphine no matter what you do at Venus's temperatures and pressures. You'd have to have some extreme scenario that doesn't fit what we know, like very explosive volcanism, a lot of water in the Venus mantle. You have to push everything to get phosphine. So that's where we're at with Venus. And I just want to put this to you right now. Can we ever claim a robust discovery of exoplanet signs of life? We imagine a future where the first two are checked. Yes, it's a real the signal is real and robust. Yes, we can identify it with the right molecule. I'm confident we can all work together to make that happen. But given all the unknowns, remember the sub-Neptune-sized planet story I told you? We had some ideas of what it could be. It looks like it's something completely different. We're still working through all we have based on the mixed up atmosphere data and the spatially unresolved planet. Can we ever claim a robust discovery of signs of life? And that's a career crisis right there. So while mulling over this question, let's take like a mini mental break and talk a bit about Venus just for a minute. So it turns out this idea and why the phosphine on Venus in part got so attacked is it's just so insane to imagine life on Venus. We know that Venus has a carbon dioxide atmosphere, a massive greenhouse atmosphere, making the surface too hot for any life we can ever conceive of. It's 700 Kelvin at the surface. And here's an artist's conception of Venus. But just like on Earth, if we hike up a mountain or go in an airplane, it gets colder and colder. And so 50 kilometers above the surface of Venus, it is the right temperature for life. Also, it's like the same pressure as here on Earth. And there are clouds there, very extensive clouds that are 20 kilometers thick. They're always there and permanently cover the planet. And did you know that on our Earth, we have life in our clouds? Bacteria get swept up from the surface, they stay in the clouds for a short period of time, eventually they get rained out. So okay, I'm obviously selling here. It sounds good, right? I mean, and this is what we think prompted Carl Sagan over half a century ago to first propose there could be life in the Venus clouds. But at that time, people weren't aware the clouds aren't made of friendly water. They're made of acid, sulfuric acid. Has anyone ever, I don't know if you've worked with sulfuric acid. It's super dangerous. You have, yeah. I'll just tell you this. So it turns out that no one had really studied this. They just assume it's impossible. And the reason is sulfuric acid destroys our life. If you put it on your clothes, it would burn a hole. It will burn a hole in your skin. None of our life can survive in sulfuric acid. It does very, very bad things to our life. But I want to share with you, my mini mental break from exoplanets has been working with sulfuric acid and exploring whether or not some other kind of life might survive in sulfuric acid. Now, we're not creating a crazy kind of life in the lab, but we're on to a super ginormous, huge journey of incredible excitement. And I'm just digressing for a minute from exoplanets to just share a few brief things with you. We took our amino acids, our 20 biogenic amino acids, we put them in sulfuric acid. One of them was unstable, with one exception. They're all stable over months or longer. Half of them are chemically modified by the sulfuric acid, but these amino acids are literally stable. Our DNA is unstable due to the sugar molecule. But our nucleic acid bases, ACGT, adenine, guanine, the ladder of the DNA, stable for over a year. It gets protonated on the nitrogens, stable. This is the tip of the iceberg of a brand new field. And it is incredible and bold, hopefully not arrogant, to want to propose sulfuric acid itself, not water, but sulfuric acid as a potential solvent for life. We have work showing that lipids, like fatty acids, lipids with a polar head, put them in sulfuric acid. You have to get the recipe right, but they point that polar head out to the very polar solvent, and they form a little spherical vesicle, like cell size, but super primitive. And all of this work, we sometimes say, well, there's no brand new idea. People had tried this decades ago, not for Venus. They didn't know it had sulfuric acid, but honestly, just for exploring science. And so a lot of this work, not the amino acids, but some of the other work, we see hints of it back in the past, that if we weren't so siloed, planetary scientists, astrobiologists, astronomers could have created this whole story. So I have my own laboratory now. I have some students and postdocs, and working really hard on this problem. And there are just so many, it's going to be a long journey. I'd love to tell you more about this if you ask in the Q&A. So what are we doing about this? We're going back to Venus, and I'm very proud to be leading a series of largely privately funded missions to Venus to search for signs of life or life itself, while it's still very taboo for large government agencies. And our first mission is called the Rocket Lab Mission to Venus. It's just a small mission. It won't find signs of life, but it will generate this way to complement traditional space missions and sending smaller, faster, more focused missions to Venus. So we had that mini mental break. I'm going to wrap up with this. I don't know if you had brain space to think about this question in the background, but we're now back to exoplanets. Can we ever claim a robust discovery of exoplanet signs of life? Well, instead of giving you the answer to that, we don't know the answer, I want to give you a few options. One of them is to make incredibly detailed computer models of all possible false positives for biosignature candidate planets. It would take way too long for me to unpack this for you, and I'm still trying to articulate it myself. So I just threw up this flowchart from a paper I really like, with the caveat that this would be a huge journey to embark on, and we can't observe the interiors of planets, but we do have experiments, petrology, like experiments we can do for mantles. We study the deep interiors of planets. We want to get the whole picture of planets. Could they have a reservoir of water that slowly leaks out, so even if the atmospheres are wiped away, billions of years later they could reform one? There are a lot of questions here. There's a lot of people working on small pieces of this, but nothing comprehensive. Another idea, let us find the true Earth twin. We cannot do that with transits, but there are many ideas in the works to do this. We have the NASA Habitable Worlds Observatory. We have the Starshade concept. We have LIFE, which is the Darwin reinvention. We have our large ground-based telescopes. A third option is what we call technosignature gases. These, they'll still have some of the same problems of false positives, but for example, life on Earth, and we think elsewhere, completely avoids fluorine. The fluorine atom, it's so electronegative. When it gets on, it's like more supergluish than superglue. It is so stuck on. Life was really no reason to use it, because if it wants to use it, it has to have a way to get it off. It does use it occasionally, but very rarely. So there's this whole field blossoming now of technosignatures, so we can explore whether there's a way to be more sure it's by, in this case, intelligent life. But what this really boils down to, and what has happened all throughout the history of astronomy, are new paradigms to get us to the next level. So for anyone here in the audience, I want to say if you're under 25, if you're under 15 and under especially, we're counting on you to think of the next paradigm. And this is because our search is a generations-long search. We're very confident we will find biosignature gas planet candidates, and we can assign probabilities. But what will ultimately take are new ideas, such as the Solar Gravitational Lens Telescope, which will be able to, if possible, spatially resolve a distant planet to 10 or 20 square kilometers. We have a lot ahead of us in our future. So we're here to celebrate the Kavli Prize, but there are literally decades ahead of us of a very exciting journey. So thank you for your attention, and I wish you all clear skies and an exciting journey of your own.
Thank you again. And we have some time for a Q&A. So are there any cues?
Do you want to? Yep.
Yeah. Maybe.
Well, while I'm here, I'll ask the first question. So my question is to Dave, because I have this microphone.
Okay.
Okay, so I think I interpreted your slides correctly, that within 15 parsecs and the small stars, there are no transiting planets receiving the right amount of energy if we're assuming the planet has to have the right amount of energy like our Earth does to be habitable. Is that what your slides showed?
No, there are some. So for example, the TRAPPIST system has...
No, but within 15 parsecs.
Yeah, it's within 15 parsecs, yeah. So there definitely are some. We just haven't been able to determine whether they have atmospheres yet because they produce less infrared light.
Right,
It's going to take more data with J2ST.
I see, okay.
Yeah, so that's very much ongoing.
Got it.
Yeah, just the hot ones.
Okay. Thank you. Just a second, there's a microphone coming.
It seems like all researchers working on life on exoplanets make two assumptions that they never talk about, which is that the orbits of these planets are going to be stable for hundreds of billions of years, and that there are no nearby cataclysmic events. Do you have evidence of either of those being true or false, or do we not know?
Well, we do. We have this thing in astronomy where it sounds like a joke, but it's quite serious. If we see the orbit, the planets, they are stable because they're just there orbiting and they've been there for a long time. But people do simulations. If there are any planetary systems where we know most of the planets, they can simulate it and see if they're going to be stable for billions of years. So there's that. Yeah, there may be a catastrophic event like nuclear winter or meteorite that destroys everything.
Yeah, I mean, the solar system is fascinating, right? It is marginally stable, right? So if you integrate, if you take everything we know about in the solar system and you integrate it forward, it is sort of just hanging in there, but it could go unstable, basically due to very small perturbations. So it's fascinating. But exactly, we do see much old. I mean, we know of stars that are 10 billion years old, and they have terrestrial planets. So there are planets out there. It's sort of like a time machine. We could study what would happen to the Earth in another 5 billion years, because that's the magic of astronomy. You can find old examples of yourself and young examples of yourself.
There's a hand, yes.
Great talks. Thank you very much. So I said, wonderful talks. Thank you very much. Very inspiring. So what's the effect of having companion stars in what you're doing, especially you, Dave? Most of the stars have another binary star, and a lot of those can be very close companions and even degenerate companions. And so how does that muck up your observations? And yeah. Can you
Yeah, right. So one thing we've learned a lot about in the universe is stars through the wonderful data we get from searching for planets. And we now know the rate of binarity of stars very well. The rate of binarity, the fraction of stars that have another star as a companion, goes down with stellar mass. So for sun-like stars, typically half the time they have a companion star. Ours is a singleton. But once you get down to these low-mass stars, it's only 20% of the time. Most of them are singletons. So actually, they're mostly isolated. If you do have a companion, yes, we think that's very disruptive to planets because the disks out of which the planets form are disrupted due to the dynamics of the star ripping material out of the disk on a time scale commensurate with when the planets are forming. However, we do know from the Kepler mission of a number of circumbinary planets. We actually do see planets orbiting binary stars in regions where they would be dynamically stable. So we do actually know of quite a few of these. So the fundamental architecture is incredibly diverse.
One thing is, for habitability, life is more creative than we are. It's probably not, I'm sure people here have read Three-Body Problem. It's not that bad. So we don't think that's a problem. But what is challenging that we usually don't mention is for the sun-like stars, and in the future we want to find the true Earth twin, it's an incredibly challenging problem because our Earth is 10 billion times fainter than our sun in reflected light, and we need to block out the glare of the sun, the star. And we don't have a way to do that for binary stars. So effectively, in our search for the Earth twin, we're throwing out right now half of the stars or more.
Yes.
Thank you for very good talks. I have one question. First of all, you're very optimistic in many of these things. You, especially David, may not find anything of what he's looking for. But why do you not look even further out in the Planck spectrum for the temperature of a star behind, of a planet behind and in front? Because the signature will be better the further out you come in wavelength, if I remember rightly.
Yeah, right. So first of all, I think my approach to this is not to begin by hoping that things are like the Earth, because I agree, then one is disappointed when one finds diversity. I think instead, I really do recognize that in all fields of astrophysics, the universe has always been more imaginative than we are. And so we need to find planets that became Venuses, and probably now their surfaces are uninhabitable, because that teaches us about the process of how planets have a runaway greenhouse effect or don't. We need to find planets that don't have atmospheres because we learn about atmospheric escape, and that teaches about the planets where they do have atmospheres. So I don't get disappointed. I just think to myself, oh, way to go, universe. But in terms of your idea, you're exactly right. As you go out to longer and longer infrared wavelengths, then the contrast gets more favorable up to a point. That's technology driven, right? So previously, we had the Spitzer Space Telescope. Now with James Webb, we can go out to really quite long wavelengths. People are really in the middle of doing that. Yes, you can imagine even going out. I mean, at radio wavelengths, you're not seeing thermal emission, but there's lots of exciting ideas to look for the magnetic fields of exoplanets directly. So there are a whole diversity of long wavelength studies that are being pursued that I just couldn't cover today.
We'll just say being naive and hopeful 30 years ago paid off. And that's why we also need the next generation to be equally naive and hopeful. But when I hear a question like that, I'm like, yeah, go ahead and work on that. See if it goes anywhere. One thing we have, as lambda gets bigger, the spatial separation of the planet and star, it goes as wavelength over diameter. So wavelengths get big, diameter needs to get bigger. But there are thoughts of like very, very next generation futuristic constellations at radio wavelengths that could be so big, spread out and get you that diameter you need. Because the Planck, remember, it also drops off so rapidly. So you're facing a problem we can't solve today, but in the future, maybe. And just one more point to add to that. People okay, when Dave was saying our solar system is marginally stable, people have an idea that all planetary systems are marginally stable in that. Imagine you go to a restaurant and every coffee cup is so perfectly full, like to the brim. Were the waiters and waitresses so careful that they can fill everything up perfectly? Or did everything overflow and you're left with the perfectly filled cup? They think planetary systems formed overfull and stuff got kicked out. And so taking your idea even more extreme, that planets are free floating. And if they have an atmosphere, they're still going to be warm because of the greenhouse effect, and et cetera. So there's all continuum of ideas that people are hopefully pursuing.
Thank you very much for two very inspiring lectures. That was very interesting. For a chemist like me, I was very intrigued by your experiment, Sara, on the viability of amino acids in the presence of sulfuric acid. So I would ask a few questions on that.
Of course.
To some extent, I'm not surprised that the salts of amino acids would be stable over a long time, but having sulfuric acid, concentrated sulfuric acid, I would expect that anything containing an alcohol would dehydrate, and in more thinner solutions of sulfuric acid, I would assume that you would have some hydration, something going on as a result of that. Could you comment on the role of the concentration of sulfuric acid on that?
Can I comment on the role of concentration of sulfuric acid? Only from a chemist. And one of our biggest challenges in thinking about life in the Venus atmosphere is the gradation of concentration. We have pure quote-unquote sulfuric acid, which is like 98% sulfuric acid by volume, but it goes down to about 70%. And what the chemist knows that any little bit, okay, if you have any little bit of water, your chemistry is different, and we are seeing a difference. So if you read the paper on amino acids, or not on the nucleic acid bases, those are generally stable. But sometimes, for example, I'll just give you one little example. When you put the amino acids together to make proteins, we've put them, we call it homodipeptides, the two identical amino acids. There's a thing called acid catalyzed, like, well, yeah. They do get destroyed typically. But at pure sulfuric acid, they're getting destroyed in a totally new, different mechanism. So if there is life, they're going to have a challenge because the chemistry is behaving differently the more water you add. Beneath some threshold, when there's some free water molecules, it behaves differently. That's all I can really say for now. But honestly, we're trying hard to find examples that can tolerate all those different concentrations. But one thing that I always reflect on is that if anyone ever looked at protein folding or the origin of life, honestly, it seems like the conditions have to be so breathtakingly contrived for anything to work at all. I love to imagine the life on a sulfuric acid planet, and they're like, wow, how could there be life on Earth? This water is so crazy. DNA has to self-repair repeatedly, billions of times in some small time unit. So we're working on trying to find something that is stable, but of course there's a case of too stable. Your reaction should have been when I said these nucleic acid bases, they're stable for a year or more. You should have said that's too stable, because molecules need to be able to do things in order for life to be there. So it's all very much in flux. And I'll just say, if you're interested, try it.
We have one more question here.
Hi, thanks for the great talks. It's a little bit of a noob question because I don't know much about chemistry, but you're looking for molecules that exist on Earth. Was there ever any signal of a molecule that doesn't exist on Earth from the spectroscopy?
Good question. Well, what we've attempted to do was enumerate every molecule that could be in a gas form. Because in astronomy, we're looking at the atmospheres, we're relying on gases that float around and accumulate. So it's not so much one that, it could be one that's not produced by life, but we think in chemistry, we have a handle on every molecule that could be a gas. So we have looked at all of those, and those are like the 14,000. We're working through categories of molecules to see if there's any way we can sort through this enormous number of molecules. So definitely keeping an open mind, because some of the gases produced by life are for very obscure reasons, for signaling or hormones. And sure, there could be a completely different set produced by life on another world.
Yeah, and one of the big challenges we face is, we sort of have firm ideas about what it means to look for life as we know it, okay? But I think we should worry about false negatives, meaning we take a spectrum of a planet, doesn't look like it's got the sorts of things that we associate with life readily on the Earth, and such as oxygen, methane. And we say, oh, it doesn't look like it's inhabited. But of course, there may be plenty of life there. It's just a very profoundly different chemistry. And I mean, that's the sort of stuff it's just very, that's much more difficult because you don't have the ground truth of the Earth. But it's a fascinating question.
I'm going to shoot in with a question then. So to answer this question about Venus, what would you need to go to Venus to figure this out, to answer this properly?
We need to go to Venus. That's the beauty of it. We can go to Venus. We could look for phosphine, but there's several, each mission would build on the next. And what we really want to do is send a mass spectrometer to Venus. It's a very special one we've picked called Origin. It's from Bern, Switzerland, because if anyone here works with mass spectroscopy, what you do is you add a charge to the molecule and it gets separated out by mass and charge, and you can tell what the molecule is. The problem is usually you fragment the molecule and your spectra is a giant mess. And it's very hard to go back to the parent molecule. But this new type of mass spec, it very, very gently puts a charge on. And we'd like to send that. But honestly, what we really want to send to Venus, because there's this idea that if your molecule is so complex, it wouldn't be generated by a volcano or by any geology or geophysics or photochemistry. And so you're having to choose where is that line and identify these very complex molecules. And there's a bunch of other ideas, including sample return, bringing back a part of the Venus atmosphere. And we have a bunch of instrumentation projects going on at all near-term, middle-term future to assess all of this.
So within the lifetime of a, let's say, 65-year-old.
Yes, if we have enough money. Sorry. Okay, let's put it this way. If you'd like to have a little sample, anyone, of the Venus clouds on your mantelpiece, for a few billion, we can get that done.
There we go. So that I'm going to grab the last question, or maybe the last question, and that is, how about the star shade?
Sure, I'd love to chat about star shade. So we really want to find that Earth twin. It is like going on 23andMe or Ancestry.com and finding a distant cousin of a distant generation, speaks a different language, or going on 23andMe or Ancestry and you found your identical twin. We really want to do this problem. There are many ways to solve the problem. The challenge is it's almost at the edge of physics in the sense that we have to block out the starlight to 1 part in 10 billion. We have to spatially separate the planet and star. And our detectors cannot handle like the huge amount of 10 billion photons for every 1 photon. Now, I want you to think of 2 categories of doing this. One is you separate the planet and starlight. Only planet light enters your telescope. It's a very faint 30th magnitude object, but over time you can collect that. I want you to imagine another way where the light is mixed together. The 1 photon from your planet, every 1 photon has 10 billion photons from your star, it goes through the telescope. There's a lot of defects that the light is hitting, it gets all mixed up. Now you've got to separate those out. So we have those 2 methods. The star shade is the first method. It sounds so amazing. You can have a giant specially shaped screen that formation flies tens of thousands of kilometers from your telescope and blocks out the starlight so only planet light enters your telescope. This idea was conceived of in the 1960s. It was invented every decade since. It is a bit on hold right now. You need a whole separate spacecraft. It's a giant deployable. We have all the details ironed out. We have heritage and large radio deployables the defense industry uses. And so the first thing NASA, at least NASA's planning to do, is the internal coronagraph. It's much more nimble. You can point it around without moving the star shade across the sky. But now you have to deal with the light mixed together. It's all mixed together. It's all bouncing around. It's all getting... So we're still advocating star shade to go forward. There's other methods as well. And the star shade, like I said, it's been revived every decade because it's so powerful in the way that it can block out the starlight.
But perhaps expensive and...
Well, it's all expensive.
Yeah.
Any problem that is 10 billion to 1, it's all expensive.
And that's all true. But I do want to emphasize this tremendously exciting thing that has happened in the last 2 years, which is the identification that the next big priority for NASA is a mission devoted to look for these atmospheric biosignatures. It's called the Habitable Worlds Observatory, and that is a tremendously exciting thing. It's not it's not guaranteed. We all have to keep up our enthusiasm for that to really make sure that that gets funded. But if you look at the success that NASA has had with the Hubble, with the James Webb, with all these great observatories, it would be that scale of a mission. And it's just profound for those of us that have hoped. And I mean, I remember the first conference I went to on exoplanets, there was 30 people, and there were ideas of missions like that. And it really is becoming a reality now, and it's just such an exciting time.
Thank you, and let's thank our winners again.